Okay, so in general, organic reactions contain covalent bonds, which are very strong. We've already talked about this, that means that the reaction is very, very, very slow. So we are going to make our best attempt to increase the rate of reaction by doing things like using the fume hood and 12 molar hydrochloric acid. The only one that works really well is combustion. So organic molecules will burn, as you know. If you set your uniform shirt on fire, especially if it's polyester, it's gonna burn really quickly. So when you have a reaction, it can be tricky because the more you get into organic chemistry, because there are reactions that actually give a mixture of products that look almost identical. So when we get to a special kind of reaction, we're going to look at how to deal with that. And then those of you that are going to continue and maybe choose to be organic chemists in some way, then part of your job will be to separate the products and remove them. They're considered to be contaminants. So if you are making medication, for example, our body will only want one form of the product. So you can't just make a pill and not know the percentage of the major and minor product. It can have very big and detrimental impacts. So when I took like my first university organic course, we handed in a little vial with our product. We had to use distillation, which is like separating mixtures using their boiling points, and we got marked on the little vial we handed in. What was the yield? How pure was the product? Did we separate it properly? So the unfortunate ideas about unwanted products has a big impact on those of you that are going, if you're choosing to continue with this as a career or more courses or whatever. Okay, so the easiest one, because it's exactly the same as we would have done in the past, is combustion. So, and the first couple points we're already in the notes. Alkanes are less reactive than alkenes and alkynes because the single bond is strong. When you have a benzene or an aromatic hydrocarbon, they are going to be more reactive than alkanes, but the double bonds don't break. It's not really, we don't really ask ranking questions, so you don't have to worry about that. You have to worry about looking at being given a set of reactants and trying to figure out what the products will be. So if you happen to print the note off, then you'll notice there's a slide with some benzenes on it. They're going to be, just like with the naming, they get their own little kind of separate topic. And as with other topics in chemistry, sometimes, or word problems or whatever, sometimes people will say, I don't know where to start. So when you're looking for the reactive site, check for where the functional group is. So far we've done double and triple bonds. We've done OH. We've done single bonded oxygen as an ether. So look for the weird part to the molecule, and that can be helpful. The only case that doesn't really help necessarily is the first kind we're going to do after combustion, which is substitution. But when those molecules, when you have to switch or substitute, I'll talk about other ways that you can kind of make it simpler for yourself. Okay, so all organic molecules will combust. you need to remember that the other reactant will, so just like grade 11, you're given the fuel, the other reactant will be O2. And your textbook sometimes will write the Lewis structure of O2. And then, of course, the products are always CO2 and H2O. This might be the only case where you would maybe draw your reactants, but then actually write it like C9H12O whatever so that you can balance it. So again, similar to the past, whether it was grade 10 or 11, balancing complete combustion is often the most annoying. And when you have incomplete, which is not predictable products like soot or pure carbon, carbon monoxide, whatever, we're just going to focus on the products as complete combustion. So the most simple one would, of course, be methane. Which I think is what your teachers use all the time because that's the gas that comes out of our Bunsen burners. But now you know where the name methane comes from. One carbon, single bonds, simple hydrocarbon is A&E. So you have to add in the oxygen or look for it. Certainly in the textbook, they'll definitely do the Lewis structure. And then CO2, H2O, and you just have to balance it. I don't like this odd oxygen. We need 4 hydrogens. I'm going to put a 2 there. 4 hydrogens. Now we have 4 oxygens. Whoa. Balanced. Okay, alcohols will do the same thing. This time, though, there's going to be an OH. You could write C3H8O. That's fine, too. Sometimes people will write it like this to emphasize that it's an OH, but it doesn't matter. Same thing, though. Oxygen has to be, is a requirement in order to burn something. And then the products are water and carbon dioxide, and you just have to balance it appropriately. As much as there are definitely questions that have to do with combustion, most of the questions, because we already did this in 9 and 10 and 11, will be the other kind: substitution, addition, and condensation. And then when we get to aldehydes and ketones, we'll do oxidation and reduction, and that sort of rounds them out. Yes. Okay, so the first newer class of reaction we're going to do is substitution. So a hydrogen atom or a functional group is substituted by a different functional group, so the clue is in the name. If I wasn't here, somebody would have to take my place. Another thing you can look at is what kind of bonds are in the reactants. So only single bonds. If you like general formulas, I guess, like in grade, say synthesis, we would write A plus B makes AB. Then you have two compounds make two products, which is not going to be like addition will not look like that. So that's another way you can look for the difference. So when we have single bonds, then our carbon atoms will be saturated. So depending on the length of the chain, then, you know, there could be plenty of carbons, there could be plenty of hydrogens, and that does make things a little bit easier because it doesn't really matter which hydrogen you pick. All of the hydrogens are equivalent. And what we're going to produce is something called, in the most technical term, an alkyl halide. And what that means is an alkane with a halogen atom attached. Usually, we just do one because these reactions do not occur very readily at all. So yes, you can try to get these to work, but it doesn't happen very well. So why would it happen twice? All of the halogens are diatomic, but what you'll see is when we substitute a hydrogen, you're going to get a molecule that you have seen before. Okay? So sometimes what they'll do is there will be conditions for an organic reaction to occur, like a catalyst, and it's written over top of the arrow, and that has nothing to do with the reaction in terms of what molecules there are. So, for example, if it requires heat, sometimes there'll be a triangle. If it requires UV light, they'll put the formula for energy. So if you see those, so let's write one out. So I'm going to do ethane. Let's do Cl2. Actually, I like color in my notes, so I'm going to pick a different color. And I'm going to put a triangle over top of the arrow. So the arrow, the triangle has nothing to do with the balancing of the reaction. It's just a condition for the reaction to occur. You don't need to memorize that, but if you see that in a textbook question, that's what that means. Yes. H. Like Planck's constant times nu. You could do HF. Does Mr. Devine do HF? So we have ethane, which has 2 carbons. All of the hydrogens are the equivalent. I am going to pick this one here, but they are all the same, all equally not very reactive. And substitution, elimination, and condensation all follow Lewis's rules. So if you remove an atom, or if you change a double bond into a single bond, then the carbon will not have 4 bonds, and you need to either add atoms to the chain or you need to switch and substitute. Okay, so I chose this hydrogen here. I'm going to take it off, the ethane. Can I leave my molecule like this? No. The carbon on the right does not have 4 bonds. So what am I going to put there? I'm going to put a chlorine. And now I have what's technically called an alkyl halide. The chlorine is attached to the carbon chain. So whether you remember, if you like general formulas, then that's fine, but you can also figure it out. So if I took a hydrogen off, what is that hydrogen going to bond to? Yes. Yep. Do you know what HCl is? Good. So you've seen that molecule before. So when you do these reactions, you're not going to leave the hydrogen by itself. The chlorine wouldn't be by itself. Eventually, a whole ton of reactions will make water or use water as a reactant. So don't push out of your brain things you already know, okay? You could, if you forgot that this was hydrochloric acid, usually I don't ask you to name or draw the non-organic reactants or products. You could call this hydrogen chloride. You could write hydrochloric acid, either way. I'm not going to ask you to draw the Lewis structure like we did in grade 11 of HCl. You don't have to do that. Just the structures for the organic molecules. Okay, so unfortunately, the substitution examples also apply to, or reactions also apply to aromatic hydrocarbons, and they are a little bit more annoying. Okay, so benzene does not break its double bonds. So this, what I've printed here, has a double bond, the resonance structure on the reactant side and on the product side. What you do need to remember is that every single benzene technically has, if you were going to draw it out properly, okay, they would all have 1, 2, 3. So each carbon would have one hydrogen attached to it. So it doesn't really matter. All of the hydrogens.
Excuse interruption. The representative from Georgian College has arrived. Students who have previously signed up for student services are asked to go to the library now. Thank you.
All of the hydrogens are equivalent. So why, and again, a ring, right? No beginning and no end. Why did I choose the hydrogen on the right? Again, for whatever reason, your textbook loves to do that. It doesn't really matter. They're all equivalent, okay? So that is the same as a substitution when you have a straight chain. All the hydrogens were the same. I just picked one of them on the ethane. And so the first type is exactly the same as the substitution example we just did. You can choose any halogen. So in this case, I chose fluorine, and then it's going to substitute. The F goes on the benzene. The hydrogen comes off, and you get something resembling an acid. And you can follow all the same principles as before. If you've been writing the 1, you can write the 1. Because there is no beginning and no end in the chain, in the ring, then you don't have to. But you can. The second and third one are a little bit nastier, okay? So HNO3 is nitric acid, and one of the functional groups or one of the additions you could have added to a chain was NO2. And that's important because it starts to look like TNT, which has benzene in it with NO2 groups on it. So we should talk about the substitution reaction, okay? So if we have nitric acid, and I want to end up with nitrobenzene. So nitro is NO2, which is from the other day. Actually, you can even write it. So if you see HNO3 and you're going to substitute, you need to remember that's going to substitute NO2. But when we go to build our other product, we would like to hopefully make something that we recognize. So if we do some atom math and you have HNO3 and you subtract N and 2 O's, what are you left with? What's HNO3 minus 1 N and 2 O's? What's left? Good. And how do we usually write that? OH. So over here, we have HOH. And I spent a lot of time in grade 11 encouraging you to think of water as HOH. Okay? So yes, if you do need to remember, if you see HNO3, it's going to substitute NO2, but it also makes sense what the product's going to be. So that can help you. But NO2 is also from the other day as well. Okay, so don't push out of your brain things you already know. Yes. If you have nitric acid as one of the reactants, it's always going to substitute NO2 to the chain, and you're going to get HOH. Switches. So this hydrogen switches with NO2. Okay? And then the last one is arguably the worst. Yes. So I would call this the most rare. But what you can do is substitute carbon chain. So actually what happens is the H is going to be removed. And in order to make an acid, that means that this carbon chain has to be the substance that's substituted. Oops. Can you do this? 16. You can sit wherever you want. Thank you. Okay, so not unlike naming, benzene is the nastiest kind of substitution. So the next kind we're going to look at are alcohols, and alcohols are the best example of using the strategy of finding the reactive site for an organic reaction. Okay, so substitution reactions of alcohols. So you're going to use acid, and again, the stronger the acid, the better it's going to work. So we're going to be very, very careful next Tuesday, and we are going to do our best at substituting this functional group. So now I've actually even drawn the ethanol as condensed. So we are looking for where is there something on this molecule that's going to be switched? Is the CH3, CH2 a good choice? No. Those bonds are very nonpolar, very boring. However, now we have this OH, so it is going to switch. Also, if we switch this OH, and then you take a look at here, again, think logically about what would happen. If I have OH by itself, and I'm going to put CH or Cl with it, what do you think it would be made? OH all by itself, what would go with OH? H or Cl? H, HOH, okay? So again, when in doubt, make water. So I'm gonna just make this a little more colorful. So boring, carbon chain, write it down. Then we have something that needs to be substituted. We can't leave that last carbon with nothing. You put the Cl on the chain, so you're still getting an alkyl halide just like before. And you're still getting H OH. Just like before. So this reaction has produced the same type of substitution product, 1-chloroethane. This is called an alkyl halide. But alcohols are a little bit more reactive. So that's what we're going to use next week, okay? And also a little bit less smelly and a little bit less toxic. So better for us in high school. Okay, so the next class are called addition reactions. Do some better highlighting than me? Holy cow. Okay, so now we have to add atoms because we are changing multiple bonds into single bonds. So this time we have 2 compounds forming one product. But again, it follows Lewis's rules. Once you change a double or triple bond into single, the carbons in that bond will be missing a bond. So that's where we need it to go in order to be 4. Okay, so it's still going to follow the rules as before. And unlike substitution, it's going to be very obvious where the double bond or triple bond is. That's your eyes just go right to that, and that automatically makes it an addition reaction. Okay? In the examples, I've called them halogenation, hydrogenation, hydrohalogenation. I tried to follow what your textbook does in case you're a textbook reader. But if you were asked to label the type of reaction, you could just put addition. They're all examples of addition. It's just being really specific. If you're adding a hydrogen, it calls it hydrogenation. If you're adding a halogen, it calls it halogenation, but they are the same thing. Okay? So halogenation, this time I'll do bromine. We did fluorine, chlorine, and now I'll do bromine. And why always halogens? Because they are the most reactive nonmetals. So that's our best chance of getting nasty organic molecules that don't react to react, okay? So you can pick whatever double or triple bond you want. I'll just start simple. Let's just do ethane. That's not ethane. If you would like to really, really emphasize the counting so you know where the extra atoms being added will go, you can add in the hydrogens. But that's not a requirement. They're still considered basically just filler. Okay, so the double bond is going to be broken, becomes a single bond. There are 2 carbons in the double bond, which means 2 carbons will be missing a bond. So again, if that's how you would like to remember, by looking at the general type, then this is different from substitution because now we have to add 2 atoms. There is no loss of hydrogen. There's 2 reactants and 1 product. Or you can follow the organic rules of making sure carbon has 4 bonds. Okay, so it's up to you. Right away, you can just go add the hydrogens. You can also do it in steps, sort of, in your mind. I'm going to change the double bond into single bonds first. When you do that, then you look at it. Does it look right? No. This carbon has 1, 2, 3. No good. This carbon, 1, 2, 3. No good. What can we put on that carbon chain to make it 4? We are adding a halogen, and in this case, it's going to be bromine. But this time we need both because we need 2 things to make our carbon happy. And then now follow the same naming rules. So technically this should be dibromo, but if you just write 1,2-bromo, that's okay. I'll accept that. And now it's ANE because it's single bonds. So you should not have ene or ein on the same both sides, okay? Multiple becomes single. And in the end, that's why double and triple bonds originally we said, or in the general slides that we've been talking about, we've said they're more reactive because there is this opportunity to change them into single bonds. Then when you get to single, now those bonds have to just straight up be broken, which takes more energy. Okay, so for hydrogenation, I'm going to do a triple bond. So I'm going to do ethyne. And you don't need to do this in steps, but because this, I chose to do it for this one because there's a little bit more space on your page. I'll change it into double bonds and then into single bonds, but you can go straight to single bonds, that's fine. But I'll show you how it works. And again, as you're doing it, it's up to you if you're like, okay, I can see it. I know that you're just going to put the hydrogens on the chain, or you can go through and do the counting. So I'm going to change triple into double. Now both of these hydrogens are missing a bond. But then you can do it again. Yes. Not H4, but I was going to say, once you get good at this, if you're going to add it in one, write it in one step, how many hydrogens technically should we put? 2, you have to balance it. The way your textbook sort of rectifies that, I guess, is they might write excess, and then that is your clue to change it from triple bonds all the way to single. So this hydrogenation, again, if you're into biology, into health and nutrition, hydrogenated fats are extra bad for us because they are turned into straight, lie together nicely saturated fatty acids, which form more like solids in our arteries. So people may tell you to stay away from hydrogenated fats for this reason. So I've recorded these all separate, but really what I want to do is have a total. So I tried to highlight it. So this, if you could just write their total out of 24, and then if they have a blank, just leave it blank. And then this one, I think the total is 41. So again, just go like the purple writing, total it up, the pink writing, total it up.
Okay.
Does that make sense?
Yeah.
Wouldn't it be wonderful if addition reactions were always this straightforward? So in these two examples, we are adding a diatomic molecule, and that means that you're adding 2 of the same atoms. What happens when they are not the same? Then this is where we get different forms or similar products. So we are going to get what's called a major and a minor product, potentially, which is then we need to pay attention to something called Markovnikov's rule. So yes, sometimes I think in the solutions often I just write marks, okay? Named after the person who first described this. So when you have a reaction like with a hydrohalogenation, so HCl, HBr, HF, now you have hydrogen and you have a halogen. No longer do you have a diatomic molecule. We're going to do we're going to do these 3, or talk about these 3, and then the next slide has another very common one, which is, of course, water, using water to make an alcohol. So when you have an alkene or an alkyne that is not as simple as ethene, then what we need to do is count the number of hydrogens. So I'm going to draw them in this time. Yes. Sorry. So some of them I drew in, some of them I drew as ticks, and that is on purpose. So these hydrogens on the far right hand, in this case right hand, carbon, do not matter. They're not going to be added. They're not going to be substituted, nothing, because the reactive site we care about is the double bond. And the two carbons that are involved in the double bond. So when you go to change your molecule into single bonds, whoops. We have a problem. Which carbon gets the H? Which carbon gets the halogen? So the way that you decide is using Markovnikov's rule. And it's not like he just made this rule up to give us a rule as a way to name these or make the structure. It actually forms what's called the major product. So again, some of you may choose to become organic chemists, and you're going to, in this kind of reaction, you would get two isomers, one of them that follows Markovnikov's rule, and it's called the major product. So the majority, like greater than 50% of the isomer produced, would follow the rule, and then the minor product would not. So as an organic chemist, you have to know how much of each is in your final vessel, because maybe you're going to, sell the product, maybe you're going to make a pill with it, whatever. You need to know how much is of each of the isomers are produced. So the one that's called the major product is going to follow Markovnikov's rule. So it states that when you add a hydrogen halide, so two different atoms, or water to an alkene or alkyne, the hydrogen, so whether it's H from the alkyl halide or the H from water, is going to bond to the carbon that already has more hydrogens. Or sometimes we say the rich gets richer. So if the question does not specify, you're always going to follow Markovnikov's rule. The only time you would write both major and minor products is if you were specifically asked to do that. So if this was the only parts of the question you were given, you would follow the rule. So carbon number 1, how many hydrogens does it have? 2. Whoa. Carbon number 2, how many hydrogens does it have? How many? 1. Do we care about this carbon? No, it is not a part of the double bond. It's already full. It's not missing anything. We don't care. So carbon number 1 has 2 hydrogens. That means it's richer in hydrogen. It is going to get the hydrogen. Carbon number 2 only has 1. It is going to get the bromine. Not even going to color code my minor one. So when you go to do the textbook questions, if it's just a list of reactants, you figure out the products. Don't even worry about the minor. You're just going to follow Markovnikov's rule. Sometimes it actually says, like as a hint in the initial question, make sure you follow Markovnikov's rule. What that means is you need to just do Markovnikov's rule, write the major product. You're not worried about the minor product at all. Okay? So the minor product would not follow Markovnikov's rule. So the hydrogen goes on the not richer atom. And you might be thinking to yourself, oh, Ms. Todd, minor product, who cares? If it doesn't follow the rule, who cares? I'll be honest with you, this is nothing. Organic reactions are, if you get into organic chemistry, are 1,000 times more difficult than this. So there's often, your biology teacher might call them racemic mixtures, L and D, like it bends light in a different way. There's all kinds of more that you're going to do with this, should you continue. So in the next example, when we're going to produce an alcohol specifically, I'm not even going to talk about the minor product. We're just going to always follow the major, okay? Only if you're specifically asked to do both, would you do both. Okay, so let's do an addition reaction to produce an alcohol. We can do 1-propene again. If you have a favorite alkene and you want to pick a different one, that's fine. But I'm not going to write, it says adding water. I'm not going to write H2O. I'm always going to write HOH. Let's make it a Christmas OH, HOH. So if you were just given this question, write the products. Don't even worry about minor. Let's just do major. But again, it might say something like, be careful of Markovnikov's rule. It might not say anything, and you just know to follow it. Okay? So which hydrogen has more hydrogen, which carbon has more hydrogens already? Number 1, 1, 2. You could even look over here. Okay, now these two carbons that I just changed from a double bond to a single bond, they are both missing a bond. Let's check. This one, the carbon number 1, has 2 hydrogens. That means it gets the hydrogen. Carbon number 2 only has 1. It's going to get the OH, making 2-propanol. That's bad English, I guess. We have one more type, but it's actually, I really should put it before addition. I think it's actually easier, which is good. Who doesn't like that? Is your hand up? You're, okay. Okay, so the last one is called condensation. So what do you think we're going to make? Water. Yay. And what a shock. So in the other reaction that made water, you could technically call that condensation, and I would accept that answer. Okay? So we are going to have 2 alcohols. I chose really, really simple ones. Methanol. You can choose any length of alcohol, and what you're going to produce is an ether. So you do need to remember that an ether is the oxygen in the middle of the 2 carbon chains. So and it's not like alcohol number 1's like, okay, I'm going to keep my oxygen. You give away your OH. I'm just going to give away my H. So that doesn't even matter. You just want to take away the H from one of the alcohol groups and the OH from the other one to make HOH, which of course is water, and then you join the 2 chains together. Whether you prefer condensed or not, that's fine. You can draw it out with the ticks. There is lots of space on here. If you prefer general ones, we can write it out as general. Okay, and then there is quite an extensive list of homework. Now, you do not need this homework for tomorrow's lab. You do not need this homework for Thursday's lesson either. So if you don't get a chance to complete it all tonight, that is okay. You will have lots of time you can use on your weekend too.